Today we're going to look at adding probabilities. And the learning target is that you can find the probability of inclusive events and mutually exclusive events, which we will talk about. All right, so on the board here, on your notes, you can see that to find the probability here of spinning a purple and then spinning a blue on these two spinners, you need to find the probability of both events occurring separately. So what we want to know is what would be the probability of spinning a purple, okay? Well, if you spin here, you can see that there is 6 equally likely outcomes, only one of them being purple. So our chances of spinning a purple here would be 1 out of 6. The chance of spinning a blue on this other spinner has 4 equally likely outcomes, 3 of them being blue, so our chance of spinning blue would be 3 out of 4. Okay, and in this case, spinning a purple and then spinning a blue are independent events because spinning one spinner has no effect on spinning the other spinner. Well, what we're going to look at now is what would be the chance of spinning a purple and a blue? We talked about this yesterday, or the last notes, when we looked at anytime you see the word and, you should be thinking multiply. Almost always in probability, we do multiplying. So if we want to find the probability here of doing the purple and the blue, we knew purple was 1 out of 6. We just had that. Blue was 3 out of 4. If we multiply those together now, that would be the probability of spinning both. Remember when you're multiplying fractions? Multiply straight across the top, the numerators, straight across the bottom of the denominator, so we get 3 out of 24, which is the same as 1 out of 8. We'd have a 1 out of 8 chance if we spun both to have both occur. Well, today we're going to look at a different situation where they might ask, what's the probability of spinning a purple or spinning a blue? If you see the word or, that means you don't need both to happen like in the last one we just looked at. And means both have to happen. Or just means one or the other need to occur. Okay, so for this one, when you see the word or, that is what is called a mutually exclusive event. These two events cannot happen at the same time. Example would be drawing an ace or drawing a 2 from a standard deck of cards. These two things, an ace and a 2, cannot be both things. Just like here, these spinners don't have anything to do with themselves. They're exclusive from one another. So if two events, A and B, in this case the two spinners, are mutually exclusive, then the probability that A or B occurs is the sum. So means we're going to add here the two probabilities. So we got to just add, what's the probability of the purple? 1 out of 6. What's the probability of the blue? 3 out of 4. If we add those up, that should be the probability of one or the other happening. Now here, when you're doing this, adding fractions is different than multiplying. Multiplying is easier. Adding or subtracting, we need common denominator. So to add these up, we need to get a common denominator between 6 and 4. A common denominator between 6 and 4 would be 12. Both of those numbers go into 12. So let's multiply this first one by 2 over 2. That's like multiplying by 1. And the second one, let's multiply by 3 over 3. Okay, that's okay to do. We're just multiplying by 1. We're just changing what the number looks like, not the value. So now this would be the same as 2 out of 12 plus 9 out of 12. Now we can add those up because we have a common denominator. If we add 9 twelfths plus 2 twelfths, add the numerators, you get 11 out of 12. Very likely chance that we get one or the other to occur. So just to test it here, if I spin, did I get a purple? Yep, looks like we already got it. Don't even need to spin the other one. So you're very likely a chance that one or the other happens. So anytime you have mutually exclusive, means one thing has nothing to do with the other, You just add them up. One or the other, add them up. Let's take a look at some of those types of problems. In this first example, it says one teacher must be chosen to supervise a senior class fundraiser. There are 12 math teachers, 9 language arts teachers, 8 social studies teachers, and 10 science teachers. If the teacher is chosen at random, what is the probability that the teacher is either a language arts teacher or a social studies teacher? All right, in this problem, a language arts teacher is not going to be a social studies teacher. Those two things are mutually exclusive. Okay, they're different groups. So or is telling us one or the other, just add them up and see what it is. So it looks like we have 9 language arts teachers and 8 social studies teachers. We want to add those up out of the total. Well, if we add them up, we get 17. We do need to figure out how many total teachers here, though, to finish answering the question. Looks like if we add up all these teachers, 8, we got 8, 12, 10, and 9, that there is 39 total teachers. So both of these would be out of 39. So we have a 17 out of 39 chance that the teacher would be one, either a language arts or a social studies. When you're answering your question, that answer is okay. If they'd want it as a percentage probability, then you just have to do some dividing. 17 divided by 39 would equal this. Remember, you got to move the decimal point over 2 times, or you can multiply by 100 to change it to a percentage. So this would be the same as about 43.6%. So pretty close to half chance that it happens. Okay, next one. Number 2 here says there are 7 girls and 6 boys on a junior class homecoming committee. A subcommittee of 4 people is being chosen at random to decide the theme for the class float. What is the probability that the subcommittee will have at least 2 girls? Okay, so that's what we need to figure out, at least 2 girls. Now, we got to figure out, what does at least mean? At least means 2 or more. We need 2 or more girls on this committee. Well, if there's 4 people on the committee, that means the possibilities here would be that we'd have 2 girls on the committee. It could also mean that we have 3 girls on the committee. It could also mean that all 4 people on the committee end up being girls. So we could have 2, 3, or 4 girls. This is an or problem. Okay, and even though it never mentioned or in the problem, 2 girls or 3 girls or 4 girls, all 3 of these situations make this true. So we got to find what's the probability of ending up with either of these 3 situations. Okay, so what we need to do on this one is figure out what's the chances of selecting 2 girls, 3 girls, or 4 girls. Well, we could find that using some combinations here, because we don't care the order we're selecting. We just want to know how many ways of selecting those 2 girls, or the 3 girls, or the 4 girls. But we'd also have to combine in the different ways of selecting the rest of the committee. Okay, if we select 2 girls, that also implies that 2 boys are being selected here. If we select 3 girls, that also implies 1 boy is being selected for this one, because we have a total of 4 people on the committee. If we end up with 4 girls, then that is everybody. No boys get chosen. So we have to also factor in that when we're doing this problem. So let's try it out. What would be the way of selecting? We'll start with 2 girls. How many ways can we select 2 girls? Well, this is a combination. We don't care the order. Okay, there's 2 girls that we're selecting, so that's the second number. Out of how many total girls? We know the total number of girls in the committee is 7. So we would do a combination of 7, choose 2, it tells the number of possibilities. Now, we need to include with that the boys, though. Okay, the 2 boys. How can we get those 2 boys? Well, for boys, there's 6 total boys. We're also selecting 2 here, and this would be another combination out of the total. Okay, total would be selecting 4. We're selecting 4 people from this committee. We've talked about that already. Out of how many total? Well, if we add 7 and 6, there's 13 total people on the committee. Okay, or tells us we're adding. Okay, now we got to do another one for 3 girls and 1 boy. So if we're doing 3 girls, that'd be a combination of 7 girls selecting 1, or sorry, selecting 3. And for the boys, there's 6 boys selecting 1. How many ways can we do that? Over again, the total of 13 selecting 4. Okay, or again, so plus, we got to do it one more time. Bottom's going to be the same again. We're still selecting 4 people. How many ways can we select 4 girls? 7 girls selecting 4. Here we don't need to include one for the boys because this situation doesn't have any boys being selected. So now we'd have to calculate all these out and then add them up to see what our total probability is. Remember how to do these on the calculator. You have a probability menu you can go to. So like if we're doing this first one, what's the combination of doing this? Make sure you enter the first number, so 6. Select your combination of selecting 2. That would be 15 ways here to do this one. Okay, let's do the next one. So if you do the combination for the next one, we have 7 girls. How many ways to select 2 of them? Looks like that would be 21 ways. Over, let's find the total one. So we have 13 people. How many ways to select 4 of them? When order does not matter, we get 715. Okay, now you got to do the same thing for these other ones. All the bottom numbers should end up being the same thing of 715 because they're all doing the same combination. And if you keep going, you should get these other numbers filled in here, and then we can calculate it out. So what we got to do is figure out what are those other combinations. Doing that, I'll let you guys try that out. Once you got them, then you want to multiply this all together. So once we have these numbers, you want to multiply. What's 15 times 21? And see what you get. Looks like this ends up being 315 out of 715. Okay, then we have to multiply this next one and the next one, and once we got all those, add them up. Why don't you try these other ones, see what you get, and see what comes out for the final answer. So pause it, try it, and then we'll check it here in a second to see what you end up. All right, let's see what you got. If you figured out these other ones, you should have got these numbers here. Multiplying, that's 210. This last one comes out to be 35. Now we can add these all up, and we already have a common denominator here, so we don't have to worry about doing that. We just need to add the numbers on top. If you add all the numbers on top, it should come out to be 560 out of 715. So that would be the answer. If this were like an ACT type question, you'd probably want to simplify that down and see what that is as a simplified fraction. Your calculator can help you with that. If you type in 560 divided by 715, this will give you the approximate percentage. It looks like it's going to be about 78.3%. But if you want it as a simplified fraction, if you hit your math button and then this first selection 1 is fraction and then hit enter again, it'll tell you the simplified fraction. Looks like this fraction reduces to 112 out of 143. So that would be the simplified fraction answer. If they want it as a percentage, it'd be about that. Okay, that one's a little bit harder when you're selecting from different types of groups. Then you have to use combinations to see how many possibilities it is. All right, the other thing that you could get in OR problems is what's called an inclusive event. That's when two events can happen at the same time, or two events are not mutually exclusive. An example, drawing a king or spade from a deck of cards. It's possible to draw a card that is both a king and a spade. There's a card that is a king of spades. So when something can be in both groups, that's called inclusive. Okay, here's kind of the difference. That mutually exclusive one we talked about before, the problems we were just doing, if you want a diagram, that would be, here's event A and event B. They're totally different. There's nothing in common about the two groups. Okay, whereas inclusive looks like this. You got group A, you got group B, but there is some things that are in both groups. We don't want to count those types of things twice. So when you're doing inclusive events, you still want to add the two probabilities, but we also need to subtract out anything that could be both. So anything that is both needs to get subtracted out. Okay, that's inclusive. Let's try some of those types of problems. Number 3 here says, suppose that 1,400 students, out of that many total, 550 take Spanish, 700 take biology, and 400 take both Spanish and biology. What's the probability that a student selected at random takes Spanish or biology? So we can see it's an or question, means we're going to be adding. Okay, Spanish, what's the probability someone takes Spanish? 550 out of 1,400. Or means add. Biology, we can see pretty easily it's 700 out of 1,400, or half the students are taking biology. But these 400 students that are included in both this count and this count are being counted twice right now. We would get an overestimate of the probability if we just added these up right now. So what we have to do is minus out that 400 students, or else our probability is going to be too high. What this looks like, we have our Spanish kids here, we have our bio kids here, and right here are those 400 students that are in both groups. So we don't want to count them twice. So we need to subtract them out. All right, so now if we figure out this should give us our probability that we're looking for. Here, we're adding and subtracting fractions. We do have a common denominator of 1,400, so that's just going to stay on the bottom. We just have to add the numbers on top and subtract. So if we add 550 and 700 and then minus 400, we should end up with 850 out of 1,400 students. Okay, if you reduce that, 850 divided by 1,400, it looks like it's about 60.7% as a reduced fraction. That would be 17 out of 28. Practice reducing, because a lot of times on like the ACT, when you take that, if they want it as a percentage, you should be able to get that, or if it's a reduced fraction, you should know which one to match it to on the multiple choice. All right, why don't you pause the video, try this one out. This is another inclusive problem, see what you get. All right, let's see on this one. You have 1,200 for that subscriber, plus brand B, there's 500 out of 2,400, but minus, there's 100 people that have both. We got to minus that or subtract that number out. So if you calculate this out, you should get 1,600 out of 2,400. That simplifies to a 2 out of 3 chance, which is the same, about the same as 66.6%, roughly equal to that. So either one of those two answers. All right, the last ones we're going to do, we're going to just try to work on getting you guys to figure out now which type are you doing. Out of all the problems we've done in the last 2 lessons, which way is the best way to do this one? So let's try a few out here. It says, what's the probability of drawing a jack out of a deck of cards, standard deck of cards, or a spade? Or, think about or a second. What's that telling us? Or is plus, adding. So what we got to figure out, is this going to be mutually exclusive or inclusive? Do these cards have anything to do with each other? Well, here's our jacks right here. All these cards are our spades right here. Is there any overlap in the two groups? Yes, you can see here there is one card, the jack of spades, that is both. So that means we are doing right here a problem that is inclusive. There's overlap here. We got the jack of spades as our overlap. So we're going to have to add these and then minus out that one card. So for this one, jacks, we can see there's 4 out of a total of 52 plus. Spades, there's 13 out of 52 minus our one overlapped card here that we're counting twice in both groups, so we don't want to count that one twice. So if you look, we got a common denominator of 52. If we add the numerators, 4 plus 13 is 17, minus 1 is 16 out of 52. So there'd be a 16 out of 52 chance, which is the same as, if you reduce it, I think 4 go into both of these numbers, it'd be the same as 4 out of 13. Or that is about 30.8%. Okay, so that's an example of another inclusive problem. All right, let's look at another one. What's the probability of drawing a queen and then a jack if the first card is not replaced before drawing the second? Okay, well, this is not an or problem. We see the word and in here. We should be thinking multiply on this one. Anytime it's an and problem, we're going to multiply. Okay, so we got to look. Here's our queens right here. Here's our jacks. Okay, do these have anything to do with each other? No, they're separate groups, so this would, we don't have to worry about anything there. And then also, if it's not being replaced, the card's not being replaced, is this going to be independent or dependent? This would be an example of a dependent. When things are not replaced, your probability changes for the next draw. So we got to figure out, what's our chance of drawing a queen? Well, we can see there's 4 out of 52. Okay, what's our chance of drawing a jack next? Well, there's still going to be 4 jacks in the deck, but now we're down to 51 cards if we selected a first queen. So the probability here, we want to multiply across. When you are multiplying, you got 16 out of a total of, this is going to come out to be 2,652. And then if you simplify that, that's the same as 1 out of 221. Or about, it's a pretty small percentage, about 0.45%. Not very likely that that happens. Let's try another card problem. What's the probability of drawing a 2 or a king? Or, that should tell us plus right off the bat here. Here's our 2s. Here's our kings. Is there any overlap here? No. This is a problem where we are mutually exclusive. These two things are separate from one another. So our number of 2s, we got 4 out of 52 cards that are 2s. Kings, we also have 4 out of 52 cards being kings. If we add that up, that's 8 out of 52. Okay, if we reduce that, 4 goes into both of these. 4 goes in 8 twice. It goes into 52 13 times. 2 out of 13, or that's about 15.4%. All right, one more. Let's try one more card problem here. What's the probability of drawing a face card and then an ace if the first card is replaced? Okay, well, and tells us multiply. Okay, we got to find the probability. How many face cards? Face cards, anything with a face on here, looks like there's 12 out of 52 cards. Okay, then what's the probability of drawing an ace? Well, they're saying that the face card is getting replaced, it's getting put back in the deck. So there's still going to be 52 cards. These probabilities are going to be independent of one another, because the chance of the second one should be the chance of this out of the same amount as the first one. And there's 4 aces in a deck, And so if we multiply these together, you're going to get 48 out of this many possibilities. That's the same as 3 out of 169. Or that's about 1.8%. All right, try some of these now on the practice